Alright, well today we're going to run through the CIE examination for physics. This is paper 2, the multiple choice paper, and the code for it 0625/21. This is May-June 2017. Alright, let's face down this enemy. Question number 1. What is the most accurate and precise method to measure the thickness of a coin? Alright, coins are pretty small, so we're going to want something that can measure small things well. Now, first option A, micrometer screw gauge. That is excellent for measuring small things. Use a ruler and look at the scale perpendicularly at 90 degrees. Well, you'd want to do that if you use a ruler, but a ruler will only give it to you to the nearest millimeter. A micrometer screw gauge does it to the nearest micrometer, so it's a lot more accurate. So if that's not as accurate, use a top pan balance. Well, that will tell you how much the weight of it is. No use at all there. Use the displacement method with water in a measuring cylinder, and that may help you begin to find the volume of it. No, that's no use at all. So the answer there is A, use a micrometer screw gauge. Question number 2. On Earth, a ball is dropped and falls 2 meters in a vacuum. The acceleration of the ball at 1 meter is 10 meters per second squared. What is the acceleration of the ball at 0.5 meters? Alright, interesting question this. Why? Because if you're rushing and you read it through too quickly, you might assume they're asking you to find something to do with the speed. They're not. They're asking you to find the acceleration of the ball. If we come down here, they're asking for the acceleration of the ball at 0.5 meters. Well, key points in a vacuum. So if it's 10 meters per second when it's at 1 meters, it's going to be 10 meters per second squared when it's at 0 meters, 10 meters per second squared when it's 0.5, at 1.5, at 2, it's going to be 10 meters per second squared for all of those areas. The answer is B. Go through the questions carefully as you do them. Question number 3. A skydiver reaches terminal velocity, then he opens his parachute. What happens to the skydiver as the parachute opens? A, there is a decrease in weight. B, there is an acceleration upwards. C, there is an increase in speed. And D, there is a movement upwards. Ooh, tricky question. Alright, let's knock out what we know it isn't. The weight remains the same. The weight doesn't change regardless of what you do in this situation. There is an increase in speed. If that was the case, people wouldn't use parachutes when they go skydiving. That would seem self-defeating. There is movement upwards. No. They're falling down. So that leaves us with there is an acceleration upwards. There we go, which is actually the answer. However, let's just talk about that a little bit briefly. Here we go. Under normal situations, you've reached terminal velocity, which is what's stated here, terminal velocity. The force upwards, which is the force due to air resistance, is equal to the weight down. So the resultant force equals 0. And as F equals ma, there is no acceleration because of that, which means that the speed, or the velocity in this case, is a constant value. That is terminal velocity. Now, here's the thing. The force due to the resultant force is equal to, say, the force of weight minus the force of the air resistance. When our little dot here becomes a dot with a parachute, then our force due to air resistance becomes much bigger, and our force due to the weight remains the same. What happens then suddenly is we have a resultant force which is not equal to 0, so that gives us an acceleration. In fact, the resultant force in this situation is upwards, which means actually there is an acceleration upwards because F equals ma. If the force is upwards, the acceleration is upwards. That's why it's answer B. Tricky little question, that one though. You can work it out by just analysing the answers, but it's a tricky one to run through and to explain properly. That's what happens, and that's why it happens. 4. A piece of steel is taken from the Earth to the Moon for an experiment. The gravitational field strength on the Moon is smaller than the Earth. What statement about a piece of steel is correct? So it's asking us about mass and about weight. What do we know? We know that weight equals mass times gravity. We're told that the gravitational field strength on the Moon is smaller than on the Earth. So we've taken this mass from Earth to the Moon. So the weight on Earth equals the mass times the gravity on Earth. But if we go to the Moon, gravity is a smaller value, which means the weight is a smaller value. So it weighs less on the Moon than on the Earth. The mass doesn't change. It doesn't matter where you are in the universe, the mass will remain the same. So it's not that, and it weighs less because the gravitational force, or the gravitational field strength on the Moon is less. 5. A measuring cylinder containing only water is placed on an electronic balance. A small, irregularly shaped stone is now completely immersed in the water. The diagram shows equipment before and after the stone is immersed. Okay, let's come down slightly so we can see that a bit more clearly. There we go. And we're being asked, what is the density of the material of the stone? Alright, so we're being asked about density. Density equals mass over volume. So we need to find the mass of the stone and the volume of the stone. So let's look at that. The mass of the stone will be 217.5 minus 105. And the volume will be given by 65 minus 40. So there we go, don't forget the units, grams and centimetre cubed. And that will give us 4.5 grams per centimetre cubed. Answer C. 6. A boat is travelling at a steady speed in a straight line across the surface of the lake. Which statement about the boat is correct? Okay, resultant force in direction of motion. So it's asking us about resultant force for all of those options. There we go. Resultant force is just mass times acceleration. If it's moving at a steady speed in a straight line, then the velocity is constant. So that means the acceleration equals 0. So the resultant force equals mass times 0, which of course is just 0 newtons. There is no resultant force. The resultant force is 0. Question number 7. A ball of weight 1.2 newtons drops through the air at terminal velocity. A sudden gust of wind exerts a horizontal force 0.5 newtons on the ball from the left. Which diagram shows the resultant force on the ball while the wind is blowing? Ooh, let's see. Alright, so we've got a force upwards, which is a force due to air resistance. We've got a force downwards, which is a force due to the weight. They're exactly equal to each other, so they cancel out. They're in opposite directions. And finally, we've got a force coming in of 0.5 newtons, which is due to the gust of wind. There we are. So the resultant force is given by C. It's just the value of the 0.5 newtons because the 1.2 newtons cancel out. Now you may be tempted to say it's one of the other ones because it should be a triangle shape. What you do whenever you add these forces together and you're drawing a diagram is you draw your first force. Here we go, we've got 1.2 newtons here. Then you draw your second force from the end of the first one. So we can come straight back. We end up back at the beginning, that's 1.2 newtons, the opposite direction. and then we end up with 0.5 newtons. Here we go, everything else just cancels out. Now the beauty of resultant forces, of course, doesn't matter the order you do them in. You could have 1.2 newtons here, followed by 0.5 newtons, followed by 1.2 newtons here. You're still left with your resultant force here. Everything ends up as it does. So you start off with the beginning and it points to the end. That's there. The beginning points to the end. That's there. So the answer is C. Part 8. The diagram shows a uniform bridge 4 meters long and weighing 10,000 newtons. The bridge is pivoted at one end. A force at the other end gradually increases until the bridge begins to lift. What is the lifting force as the bridge starts to move upwards? All right. So, the first thing we want to do is calculate the turning moment that's trying to push it downwards. Here's a bridge. It's not a great bridge. It has a weight of 10,000 newtons. Well, that 10,000 newtons, we get a centre of mass in the middle. That's where it is. We get 10,000 newtons pushing down. The entire length is 4 meters, which means the distance to the centre of mass is 2 meters. And the moment, which is given by the force times the distance, is 10,000 newtons times 2 meters, which will give us a value of 20,000 newton meters. 20,000 newton meters. Now, my lifting force is right at the very end. And the question is, how big is that force when it all starts to move? Well, for it to move, the force times distance, which in this case is force times 4 meters, would have to equal at least 20,000 newton meters. Divide both sides by 4, and that tells me the force is 5,000 newtons. Option B. Question number 9. A bullet of mass 0.1 kilograms, it's a pretty heavy bullet, travels horizontally at a speed of 600 meters per second. It strikes a stationary wooden block of mass 1.9 kilograms resting on a frictionless horizontal surface. The bullet stays in the block. What is the speed of the bullet in the block immediately after the impact? Alright, we need conservation of momentum. Which is this? Momentum, of course, is mass times velocity. So the initial momentum is given by 0.1 kilograms mass times the velocity of 600 meters per second, which is 60 Newton seconds. The final momentum is mass times velocity, but both masses are together now, multiplied by this velocity that we don't know what it is. And because momentum is conserved, that will give us a value of 60 Newton seconds. So I can divide both sides by 2 kilograms, and I will find that V equals 30 meters per second, which is option A. Question number 10. A box of mass m slides down a slope of length L and vertical height d against a friction force F. As the box slides down the slope, it loses gravitational potential energy and it does work against the friction. Which rho gives the loss of gravitational potential energy and the work done against friction? Right. That's a little tricky question. The reason it's tricky is because of the labels they've used. What do we mean? Well, work done, the work done against friction, is force times distance. But d here isn't distance, d is height. The distance is actually L. So the work done against friction is force times length, FL. The loss in gravitational potential energy is given by mass times gravity times height. But of course, height here, h, is actually d, because of the way they've labelled it. So that's mass times gravity times d, which is the height in this case. So they've tried to trick us a little bit by using L and D instead of, well, H and D in different areas. Okay, so which one then will give us that? Work done, force times L, FL. That's a possibility, and that's a possibility. And gravitational potential energy, mgh, which is in fact mgd. Here we go. That's the one we want, A. Excellent. You'll see whenever I come across these sections where there are tables, I tend to put a little mark next to the possible right answers, and I just narrow them down as I move through it. It makes it easier for me. There we go. 11. The diagram represents the energy transfers for a device. The device is 50% efficient. Okay, so let's label it. I have a value of, I'll say I have 100% coming in. If it's 50% efficient, and 50% of it's useful, and 50% of it's wasted. Which equation is correct? Input energy equals useful output energy divided by 2. Well, that's no. Useful output energy equals wasted output energy divided by 2. No, wasted output energy equals useful. Well, yeah, they're both the same. And D, wasted output energy is useful output divided by 2. No. So the answer is C. 12. A student carries out some simple exercises. In which exercise is the most work done? Okay, well, work done is force times distance. And if you're lifting something up, the work done is mass times gravity times height, because mass times gravity is the weight, which is the force, so it's still force times distance. All right, A, lifting through 1 meter. Well, mgh, 1 kilogram times 10 meters per second squared, multiplied by a height of 1 meter, gives me a total energy, or total work done, of 10 joules. Pushing through 1 meter against a frictional force of 4 newtons. Okay, the force times distance, that's going to be 4 newtons times 1 meter, which is in fact 4 joules. C, lifting 2 kilograms through 2 meters. Well, 2 kilograms times 10 meters per second squared times 2 meters is 40 joules. Oh, that's out in the lead at the moment. And finally, force times distance, 2 meters times, 2 newtons times 2 meters. I'll just put that in there. There we go. It's 4 joules. So the answer, very clearly by a big margin, is C. 13. 4 different liquids are poured into 4 containers. The diagram shows the depth and the density of liquid in each container. In which container is the pressure on its base the greatest? So we're looking for pressure in a liquid. And pressure in a liquid is density times gravity times height. So let's calculate the pressure at the bottom of each one of these. A, we have a density of 3.1 grams per centimeter cubed times gravity times just 10 meters per second squared times the height of 0.1 meters. Alright, that's going to give me 3.1 pascals. Next one, we have 1.2 times 10 times 0.2, which gives us a value of 2.4 pascals. Next one, we have 1.3 times 10 times 0.3, which gives us a value of 3.9 pascals. And finally, 0.8 times 10 times 0.4 gives us a value of 3.2 pascals. Okay, so the question is, which one is biggest? Pressure on the base the greatest? Let's see, 3.1, 3.9, it's C. There we go. For those types of questions, it's always good just to recheck what they're asking for before you commit to an answer. 14. Brownian motion is observed when using a microscope to look at smoke particles in air. What causes the smoke particles to move at random? Well, A, smoke particles are hit by air molecules. Absolutely true, that's a good possibility. Smoke particles are moved by convection currents in the air. Yes, but not in a way that you'd see them through a microscope. C, smoke particles have different weights and fall at different speeds. They do, and they do. It's not what we're looking at there. D, smoke particles hit the walls of a container. Though they do, it's not relevant, however. So the answer is A. 15. Gas molecules striking a container wall cause a pressure to be exerted on the wall. Which statement explains this? Well, it's a collision with the wall, so it's going to be change in momentum. When a molecule rebounds, A, there must be a change in energy. Nope. When a molecule rebounds, there must be a change in momentum. Yes. When a molecule rebounds, there must be a change in its speed. No. Velocity, yes. Speed, no. D, when a molecule rebounds, there must be a change in its temperature. No. B, temperature goes as a measure of the random kinetic energy of the molecules. 16. Equal masses of two different liquids are put into identical beakers. Liquid 1 is heated for 100 seconds and liquid 2 is heated for 200 seconds by heaters of the same power. Each liquid has the same rise in temperature. Ooh, but one's heated for twice as long, so one's at twice the amount of energy put into it. Which statement is correct? Each beaker of liquid has the same thermal capacity. B, each beaker of liquid receives the same energy. C, liquid 1 receives more energy than liquid 2. And D, the thermal capacity of liquid 1 is less than the thermal capacity of liquid 2. Ooh. Oh, a tricky little one, this one. Alright. Let's look at specific heat capacity. E equals mc delta T. Now, when you get a fixed mass, and you know specific heat capacity, these two sometimes get changed into just thermal capacity. So that gives you E equals C delta T. That's what this is talking about. It's talking about the thermal capacity for those ones. Okay. Now, what do we know? We know that liquid 1 is heated for 100 seconds. Yes, liquid 1, so it receives an amount of Ng. Let's call it E. Liquid 2 is heated for 200 seconds, so that's got twice as much energy going into it. So this is the equation that guides it. E equals C delta T. If one takes an amount of energy E and the other one takes twice the amount of energy for the same change in temperature, then it must have twice the thermal capacity. So that tells us D, the thermal capacity of liquid 1 is less than the thermal capacity of liquid 2. That's why liquid 2 takes so much more energy to heat it. Let's run through them, the other options. A, each beaker of liquid has the same thermal capacity. Nope, they would take the same amount of energy to heat them. B, each beaker of liquid receives the same energy. Nope, one's heated for twice as long. C, liquid 1 receives more energy than liquid 2. Nope, we're told that liquid 1 is actually heated for less time. So there we go. Option D, the thermal capacity of liquid 1 is less than the thermal capacity of liquid 2. Water of mass 100 grams at a temperature of 100 degrees C is converted into steam at 100 degrees C. So no change in temperature, just water to steam. The specific latent heat of vaporization of water is 2,300 joules per gram. How much thermal energy is absorbed by the water? Ooh. Alright. The energy will be given by the mass multiplied by the latent heat of vaporization. So straightforward multiplication. Now we've got 100 grams. I'm going to do this in grams because, there we go, if you look there, the latent heat of vaporization of water is given in joules per gram. Sometimes it's given in kilograms, and that's absolutely fine too. Just make sure you're being consistent throughout. So we've got a mass of 100 grams multiplied by 2,300 joules per gram, which gives us a value of 230 kilojoules. There we are. C, 230 kilojoules, 230,000 joules. 18. A copper bar and a wooden bar are joined. The piece of paper is wrapped tightly around the join. The bar is heated strongly at the centre for a short time and the paper goes brown on one side only. Ooh. Which side goes brown and what does this show about wood and copper? Right, now this is a tricky question, and I'll explain why to you. The question being asked is related to the fact that the paper changes colour and goes brown. It's not asking about the how much it's conducting and anything like that at this point. It's relating the paper to the properties of the wood and the properties of the copper. Okay, so let's examine that. First of all, which one of these is a better conductor of heat, copper or wood? And the answer is copper, which means what? As we heat the paper, a lot of the heat from the paper goes into the copper. And what that means is that this part of the paper will be colder than this part, which is hot. And the reason why is that wood is a bad conductor. It's an insulator, a thermal insulator. Which means that the heat in the paper stays in the paper and the paper gets hotter and hotter and turns brown. So let's begin there. Let's look at our options. The brown side of the paper has to be on the wood section. Why? Because the copper will conduct the heat away and keep it cold, or colder. Prevent it from burning. Why does this happen? Wood is a good thermal insulator and copper is a good thermal conductor. The answer is D. That was a tricky question, that one. Different waves hit barriers with different sized gaps. The waves will diffract. In which diagram does the greatest spreading occur? Okay, we're talking about diffraction. Diffraction is biggest when the wavelength is very close to the size of the gap, D. Alright, so if we look at A, it's wavelength 1, gap 2. Not so great, they're not equal, the gap is twice as big. If we look at B, the wavelength is 2 and the gap is 2 centimeters. Oh, that's good. So it will definitely diffract there quite a lot of spreading. C, wavelength 1, gap is 3, so nope. And D, wavelength is 2, gap is 3. No, the best one is the one where they're equal to each other. B. 20. A converging lens is used as a magnifying glass to view an object. Which statement is correct? The image is inverted, it's nearer the lens than the object, the image is the same size, the image is virtual. Right, when you're using a magnifying glass, or a lens as a magnifying glass, you're creating a huge virtual image. It can't be projected. 21. Which diagram shows what happens when a ray of white light passes through a prism? Well, it will initially bend towards the normal line. There we go, so let's just draw this out. It will come in, it will bend towards the normal line, and then as it reaches the outer edge and goes back in there, it will bend away from the normal line. And it will spread out all the way. Every time it changes direction, it will spread out a bit more. That's what we're looking for, which is answer D. There we go. 22. Light travels in a vacuum and then enters a glass block. The speed of light in the glass block is 2 times 10 to the 8 meters per second. Okay. Which statement about the speed of light is correct? The speed in a vacuum is 1.5 times the speed in the glass. Let's see. Speed of light in a vacuum is 3 times 10 to the 8 meters per second. If I divide that by the 2.8 times 10 to the 8 it's travelling at, that is 1.5. So that's correct. Look at the other options. The speed in the glass is the same as the speed in a vacuum. Nope, not true. The speed in the glass is 1.5 times the speed in a vacuum. No. Light travelling in a vacuum is as fast as light travelling gets. Doesn't get faster. See? The speed in the glass is 1 times 10 to the 8 times the speed in a vacuum. No, not at all. So it's answer A. 23. A fire alarm is not loud enough and the pitch is too low. Then an engineer adjusts the alarm so it produces a louder note of higher pitch. What effect does this have on the amplitude and the frequency? Okay. We're going to make it louder. Well, if it's louder, the amplitude increases. So the amplitude is going to get bigger. So that's A or B then. And the pitch is higher. If the pitch is higher, the frequency increases. And that gives us answer A. 24. In a child's toy, metal fish are lifted out of a toy pond using a metal rod. The fish are magnetically attracted to the end of the rod. There's no magnetic force between the fish themselves. Ooh, right, okay. What are the possible materials from which the fish and the rod are made? Okay, possibilities, we get aluminium, soft iron and steel. Now, if these fish aren't normally attracted to each other, then they're magnetically soft. Which means they don't keep their magnetism, and that would be iron. So the fish are made of iron. The metal rod, if it's attracting the fish, must be a permanent magnet of some sort, so it's probably made of steel. There we go. So we're going to have a steel metal rod and iron fish. There we go. Possibility D, soft iron, and the rod would be made of steel. 25. What is the most effective method of demagnetizing a bar magnet? A. Placing the magnet in a large solenoid, in a solenoid carrying a large alternating current and decrease the current. That would work. B. Placing, well, it's asking for the most effective, not just will it work. B. Placing the magnet in a solenoid carrying a large direct current and decreasing current. No, that will do nothing. Has to be an alternating current to mess around with the magnetic domains in the magnet. C. Placing the magnet in a solenoid that produces a magnetic field in the opposite direction to the magnet. Nope, that'll just over time reverse the magnet. D. Placing the magnet next to an identical bar magnet with its poles in the opposite position or opposite direction. You're just giving it a friend. Don't do that. The answer is A. And that's exactly the same as putting it in a solenoid that has a large alternating current, and rather than decrease the current, slowly remove the bar magnet until it's far away. Same effect. 26. A magnet near a coil of wire is attracted to the coil when there's a current in the coil. That's nice. Which statement explains this force of attraction? A. The coil of wire has its own gravitational field. No. I'm not saying it does, I'm just saying it's so tiny it wouldn't make any difference. B. The coil of wire is made from soft iron. No, that's not really going to have much of an effect either. C. The current in the coil of wire creates a magnetic field. Well, that's true. And that would have an effect on a magnet nearby. D. The current in the coil of wire induces a charge on the magnet. No. 27. A student rubs a plastic rod with a cloth. The rod becomes positively charged. What happens to the rod? Okay. Cloth, positive, negative, positive, negative, positive, negative, positive, negative. The only way that our cloth becomes positively charged is if we lose some of the electrons. Those electrons have to then go somewhere else. They've moved into the rod. So the rod has gained electrons. Protons, of course, are in the centre of the atom. They don't move about much in terms of being exchanged. 28. What quantity is measured in coulombs? Easy. It's charge. Current is measured in amps, EMF is measured in volts, and power is measured in watts. 28. Oh, here we go. Not 28, 29. A cylinder of conducting putty has length L, diameter D, and resistance R. This putty is now molded into a cylinder of diameter 2D that has the same volume. This question is a beast. It's a bit of fun, don't get me wrong, but whoa. Okay, so let's begin at the beginning. Resistance is proportional to length over area. Area is proportional to D squared. Now, if we look at the volume equals the length times the area. If I double the diameter, what happens there? Well, the area is proportional to the diameter squared. So if I have twice the diameter squared, then I'm going to end up with 4 times the area. 4 times the area. If the volume's the same, then the length is 1/4. That's pretty harsh, but it's how we begin. So we've got resistance is proportional to L over A. So what happens if we change the length to 1/4? Well, it's L over A. We've now got 1/4 of the length. The area is now 4 times the area, which gives us 1/16 times L over A, which is 1/16 times the original resistance. Now that is a brutal question. A lot of fun. This is the reason why you don't stay with one question trying to get the answer. This one you could easily lose 10 minutes on. It's a rough, tricky question. Do it quickly, or come back to it later on. Do the easy questions first. Do not waste your time trying to get 1 mark here. So be very careful with that. Question 29. That questions like that, they are gremlins. They're waiting to steal your time. 30. The average current during a lightning strike between a cloud and the ground is 1.5 times 10 to the 4 amps. The lightning releases 3 times 10 to the 8 joules of energy and lasts for 2 times 10 to the minus 4 seconds. What is the average EMF between a cloud and the ground? Right. Okay. The EMF, which is the voltage, is the work done per unit charge. So let's get the unit of volts, which is joules over coulomb. 1 volt is 1 joule per coulomb. So let's look at this. So we're given the value in joules, that's 3.0 times 10 to the 8 joules. We want to find out the charge in coulombs. And charge equals current times time. So that's going to be, here we are, 1.5 times 10 to the 4 amps for a time of 2 times 10 to the minus 4 seconds. And that will give us 3 coulombs. So the EMF is going to be 3 times 10 to the 8 joules divided by 3 coulombs, which is just 1 times 10 to the 8 volts. There we are. So the voltage is the work done per unit charge. And looking through it, that's how we work it out. That's quite a tricky question as well. It's between 29 and 30. You could easily, if you weren't paying attention, lose 20 minutes of your exam. Do the easy questions first. Hugely important. 31. A student connects a variable potential divider circuit. What happens to the reading on the voltmeter as the sliding terminal T is moved from R to S? Ooh, right, okay. Basic bit of maths here, or basic bit of experience. If I connect this to itself, or to the other side, I'll get 0 volts. If I connect it all the way down to here, I'll get 12 volts. That's basically what's happening. Because there's no resistance in the wire, it's the same connecting it at the top as it is connecting it round here. I would still read 0 volts theoretically. Okay, so as I'm moving this down, what I should see is it move from 0 volts all the way up to 12 volts. So, B, it increases from 0 volts to 12 volts. 32. The circuit diagram shows a circuit with an AC supply, a diode, and a resistor. Which diagram shows how the current I in the resistor varies with time? Alright, what does that mean? This whole setup means that we're going to end up with a current like that being applied to the circuit. However, the diode will only let it travel in the forward direction. It won't allow any current to move in the other direction. We should end up with a graph like B. 33. A light-dependent resistor and resistance R connected in a series circuit. Light falls on the LDR. The brightness of the light falling on the LDR decreases. Ooh, okay, so that's important. The brightness of the light falling on the LDR decreases, which means the resistance of the LDR will increase. Because the more light, the less resistance. Less light, more resistance. What happens to resistance of the LDR, and what happens to the reading on the ammeter? Okay, well, First, the resistance of the LDR increases, and because V equals IR, I, which we're measuring, is V over R. This is voltage over the total resistance. And because the light's decreasing, the resistance of the LDR is getting bigger, the total resistance is increasing and the current is decreasing. There we go. So the reading on the ammeter decreases, there are possibilities, and resistance of the LDR increases. That's the only one, C. 34. The diagram shows a logic gate which input combinations at P and Q give an output of 0 at R. Now, this is what's known as a NAND gate. And a NAND gate is basically an AND gate plus a NOT gate. And that's how we'll analyze it. So we'll have P, we'll have Q, we'll have 1 and 2. And let's just put this out. P, Q, 1 and 2. We'll analyze what it should be like at each side, each section. So just a little table here, a little truth table. Best way to do these kind of things. Start with 0, 0, 0, 1, 1, 0 and 1, 1. Okay, for an AND gate, we will get a high output, a 1, if P and Q are both 1. There we go. And 0 otherwise. A NOT gate will take those zeros, 0 volts, and turn it into a 1. We'll take a low and turn it into a high. And if anyone's ever curious as to where does this magic electricity come from when you've got zeros and suddenly you've got 1, these things sit on top of a power supply. This whole circuit that they'll be attached to will have power supplies running into it. It doesn't come from nowhere, it's just they control the switching. So, which input combinations give an output of 0 at R is going to be where P and Q are both 1. This bottom option down here. D. 35. A simple DC electric motor is fitted with a coil that rotates in a magnetic field. Ooh, magnetic fields. A commutator connects the power supply to the coil. Right. It's a DC motor, so what we're going to have is a split ring commutator. What's the purpose of the commutator? Converts AC into DC in the coil? No. No, no, no. It's a DC motor. It prevents the current from becoming too great? No, it doesn't do that. It reverses the direction of the current in the coil after every 180-degree rotation of the coil. That it does do. It switches the current off momentarily after every 90-degree rotation of coil. It does not do that. And the reason it works is because split rings are just like little sections with brushes attached. There we go. Brush there, and then the electric circuit going off into the distance, and they spin round. So every 180 degrees it switches from positive to negative, or the other way around. 36. What is the purpose of a relay? Well, a relay allows you to use a tiny voltage to control another circuit, sometimes with a very, very big voltage. If you want to know what that's like, start up the car. A tiny little, you wouldn't want hundreds of amps travelling through the key that you carry in your pocket. It wouldn't melt it. But you can use a relay to control that, so your key in your car controls a little switch which works a larger, more powerful section of the car. So 36, what's the purpose of a relay? What are the options? To change a large voltage into a small voltage? Well, it is not that. To change a small voltage into a large voltage? No. To use a large current to switch on a small current? No. And to use a small current to switch on a large current. There we go. D. 37. Which row gives the relative charge of an electron, a neutron, and a proton? Okay, well, electrons have a charge of -1, neutrons have no charge, and protons have a charge of +1. So, electron negative, yep, proton 0, neutron 0, and proton +1. There we go, the answer is B. 38. A nuclide of element X undergoes beta decay. Which statement is correct? Beta decay. What happens with beta decay? Well, we start with a neutron. It gives out an electron and changes into a proton. Okay, so proton has a charge of 1 and a mass of 1. Electron has a charge of -1 and a mass of 0. And a neutron is 0 and 1. Mass of 1, no charge. Okay, so if something undergoes beta decay, what happens? The nucleon number increases by 1. No. Neutrons live in the nucleus, as does protons. Nucleon number remains the same. Yeah, that's true. The proton is, product is another nuclide of an isotope of X. No. And D, the proton number decreases by 1. No, we get one more. There we go. So the answer is B. The nucleon number stays the same. 39. A sample of radioactive isotope is decaying. The nuclei of which atoms will decay first? Nobody knows. It's a mystery. It's completely random, so no one's really sure. Impossible to know because radioactive decay is random. Be impossible to know unless the age of the material is known. No, that won't tell you anything. Other than how much there should be left. C, the atoms near the centre will decay first because why? No reason. Rubbish. D, the atoms near the surface will decay first. No. 40. A detector of ionizing radiation gives a background reading of 20 counts per minute. Ooh. A radioisotope with a half-life of 2 days is brought near the detector. The reading on the detector increases to 100 counts per minute. Okay. Alright, let's do a basic little hand-drawn graph of this. We've got a situation here where 20 counts per second, second per minute is just background. This would be counts up here per minute, and this would just be time in some form or another, days I think. Yeah, that's what the half-life is. We get background count of 20 regardless, and we bring this radioactive isotope in and we get 100, which is another 80. We get an extra 80. And what we want to do, oops, I can draw as a straight line, why not? There we go. We want to find out when the count will be 40 per minute. That's what we're interested in. So in order for it to be 40, the 80, the extra amount going in, let's see, 40 minutes of background count will give us 20, which is what we need, what we expect to get from our radioactive isotope with a count of 80. So let's see, I start with 80 and I want 20. So let's look at what happens. If I start with 80, I go to 40 with 1 half-life, which is 2 days. I then start with 40, and over the next half-life I'll go to 20, which is what I want. So this is 2 half-lives. 4 days. And that's how long it will take for the count to go to 40. So the answer is B, 4 days. There we go. And that is the end of that paper. So well done. Good job. If you liked that paper, please feel free to like and subscribe. If you've got any other papers or questions you want me to run over, feel free to leave a comment. Have a wonderful day.